All right, we've reached an important step in the creation of the diagram for 360 degrees, where we are eventually going to plot 360 points around the circumference of the circle. In this video, we're going to take these 8 circles that are making up the diameter of the larger circle, and we're going to disperse them around the circumference in such a way that they're all equidistant from the center and also equidistant from their neighbors on either side. Okay, so how we're going to do that is like this. First thing that we do is draw this geometric pattern, which divides the circle perfectly into 12 equal sections. So each of these sections is a 30-degree section. So that's 15 degrees, then 45, 75, etc. Now we're using the dodecagon perimeter as a reference for our next step. We're going to use that straight line that's perpendicular to the 45-degree line. We're going to travel along the distance of 0.5 root 2, remembering that the entire line is 4 sections of 0.5 root 2. So we travel halfway between the center of the line and the end. We put our compass on that specific lattice point and we draw that circle. We do the same thing on this side, draw that circle. So we do that 4 times. So now we've done 8 circles. How do we do the same thing down here? Well, we draw 2 larger circles now. One defined by the point created by where the 45-degree line crosses the dodecagon. So we draw that circle. And then we draw another one defined by those 2 points. So we have another circle just outside. So then we set our compass to the length of 0.5 root 2. We put it on the point where the 15-degree line is intersecting the inner circle. And then we make a mark on the outer circle. So you do something like that. And then we reset our compass to the radius of these circles, which is 0.49 root 2. We put it on the point we just determined on the outer circle, and we draw and we create a circle. And we do that on all of the remaining degree lines so that all of these pairs of circles have the same relationship to their respective degree lines as this pair of circle does to the 45-degree line. What we've done now is created a dozen pairs of circles where we know that the space between them is 0.06 root 2. And we multiply that by a dozen in base 12. And so 0.06 root 2 times a dozen is 0.6 root 2. So the total perimeter of the dodecagon is 1 do 8. 3 times the diameter, all those circles, 3 times that is 3 times 6.4 root 2, which is 1 do 7. So you subtract and get 1 unit of the square root of 2. So that's the empty space left over. So all of these pairs have half of that space between them. And so given that everything is balanced and symmetrical, we're on the 15 and the 75-degree lines, is there any way when we connect the center points of these pairs on either side that the space between them isn't also 0.06 root 2? Okay, I would say that all lines up, and this is where I would ask for help from my mathematical audience and say, is there a concise way to just sum up what we just did, given the construction of the dodecagon and the balance of that this geometric pattern brings into play, how all this works, that we can just say, therefore, the space between these pairs is the same as the space within these pairs. Remember that these lines here are inside of the 30 and 60-degree lines. So what's happened in a sense is there's a drawbridge that's closing when we connect those 2 points right there. How would you say that?